When was the last time you took a drink of water from a water fountain? Did you ever wonder where that water came from or what was in it? Sure, the water came from some pipes, but where did it come from before that? More than 50% of the water used in the United States today comes from under the ground. This water is called groundwater. In the future, more water supplies will come from groundwater because there is more groundwater than there is surface water. Groundwater in the United States is used in many ways. Approximately 301 million liters, almost 80 million gallons, are used per day. The largest amount of that is used for irrigating crops and watering livestock. Taking showers, brushing our teeth, and washing clothes and dishes makes up about 15% of the water used daily. Industry and commercial uses account for about 11% of the total groundwater use. The remaining 6% is used in other ways, such as thermoelectric power and mining. Because groundwater plays such an important part in our lives, and because it will become more important in the future, we should learn more about how this critical resource occurs and why it needs to be protected. We're going to take a look at what groundwater is, where it comes from, and how we affect this precious resource. Water is constantly being cycled through the earth and the atmosphere in a process called the water cycle or hydrologic cycle. Liquid water evaporates from streams, lakes, the oceans, and plant surfaces and turns to water vapor in the atmosphere. When the air is cooled, water vapor condenses into water droplets, which gather together to form clouds. The clouds eventually get too full of water and it rains or snows. This is called precipitation. This rain or snow falls to the earth where some flows downhill as runoff to streams, lakes, or the oceans. Some water is held on the land and plant surfaces where it evaporates. Some of the water that settles on the land surface will move through the soil surface and percolate through the pores in the soil. Some of these water molecules will be held in the pores to be taken up by plants and evaporated into the air from plant tissues. When it can go no further, the water will fill up all of the spaces between soil particles and all of the other crevices and cracks in the Earth's crust. Water which saturates the Earth's crust in this way is called groundwater. Some groundwater eventually returns to the surface through springs, rivers or lakes, and the oceans. After the water reaches the surface, it will eventually evaporate and the entire process continues. The hydrologic cycle is the way that water moves in the world around us. Precipitation is the only source for replenishing or recharging the groundwater, which is so important to us. Because water must move into and through the soil to become groundwater, and because groundwater is stored in the openings in the Earth's crust, what happens on the soil surface and under the ground will affect the groundwater. This groundwater model will help us to illustrate some of the basic ideas about groundwater. This plastic box is filled with sand, rocks, and clay, much like the earth we are standing on. Think about it as a piece of the Earth's crust. The water supply, or precipitation for the model, is added at one end of the box. As the water moves into the sand and gravel in the model, the pores begin to fill. When the pores are filled in a part of the Earth's crust, that area is saturated. The parts of the Earth's crust which are saturated are called aquifers. These aquifers store groundwater, and when groundwater moves, it moves through the aquifers. The top of the saturated zone in the crust is called the water table. We can see the water table in this model more easily if we mark the height that the water reaches in the long tubes on the front of the model. The tubes in the model are called piezometers. On the Earth's surface, piezometers are long pipes which are pushed down until they pass the water table. Piezometers and monitoring wells help us to study groundwater. If we connect a line between the top of the water in each of the piezometers, we can see the water table. The water table is a reflection of the forces which make groundwater move in a water system. The force moving water is energy. water will move from high energy to lower energy. We can measure the amount of energy at a given point by measuring the height of the water at that point. The difference in height between 2 points means a difference in energy. We measure the energy which can move the groundwater by measuring the height of the water in the piezometers. The height of the water in the piezometers is the hydraulic head. The higher the hydraulic head at any point means more energy. Groundwater will move from areas of high head to areas of lower head. Aquifers, the water-bearing parts of the Earth's crust, can be either unconfined or confined. An unconfined aquifer is open to the influences of the atmosphere. Nothing restricts the movement of air or water to the saturated zone. Wells and unconfined aquifers are affected by local weather because the aquifer is fed by local precipitation. The top part of the model shows an unconfined aquifer. When an aquifer is shut off from the atmosphere, it is called a confined aquifer or artesian aquifer. Like the unconfined aquifer, the confined aquifer is fed by precipitation. However, it gets its water from far away at a point where it is unconfined. For this reason, wells in confined aquifers are not influenced by local weather. In the model, the lower aquifer is a confined aquifer. It is cut off from the influences of the atmosphere by the confining layer of clay above it. As groundwater moves, it not only flows from place to place in aquifers, but it can also flow from springs and into streams and lakes as surface water. It is important to realize that no groundwater is isolated. All of it at some time is connected with surface water. While groundwater comes to the surface in many places naturally, it can also be pumped from wells. Wells are the source of most of the groundwater we use. The wells are drilled, driven, or dug deep into the earth, past the water table, and into the saturated zone. As wells are pumped, water travels through the aquifer, into the well, and up to the outlet at the top. Pumping creates a head difference between the well and the rest of the aquifer, causing water to flow. If the water flows into the well faster than it moves through the soil, a cone of depression forms. When we pump water out of the well in the model, the water level in the piezometers closer to the well falls further than the piezometers that are at a distance. The triangular area around the well is a cross-section of the cone of depression which forms in the water table. If we pump the well too much, the well runs dry. When this happens, we call the condition an overdraft. Overdrafts mean that not only the well which has been pumped, but other wells nearby will be without water until the aquifer can recharge. To prevent water shortages in groundwater areas, we have to learn how to control pumping so all wells using an aquifer can keep a steady supply. Water can dissolve more materials than any other liquid. This is why it's often referred to as the universal solvent. This is good when it comes to washing things, but isn't so good when someone else wants to use the wash water for another purpose. Septic waste, leakage from municipal landfills, and industrial and agricultural chemicals can dissolve in water. When they do, they can be carried to groundwater and contaminate the supplies we need for other uses. In the model, imagine that the tube we have buried near the surface is part of a septic drain field. As we add dye to the tube to simulate septic tank drainage, we can see that the drainage will move to the groundwater and may move with the groundwater to nearby bodies of water or to water supply wells. We assume that drain fields protect groundwater because the soil will clean up the waste before they reach the groundwater. We need to make sure that septic tank drain fields are properly located so that the soil can help trap the leached materials. We also need to ensure that discharge into the drain field does not overload the soil's capacity to cleanse the water. Municipal landfills are widely used to dispose of solid wastes. Water percolating through the landfill can take waste from decaying fill material into solution and carry it into the groundwater. The leachate, as these contaminants are called, will flow with the groundwater to wells, streams, or lakes and may end up in the glass of water we drink. If a landfill is sealed using the correct lining material, leaking is much less likely to happen. Watch what happens when we place a piece of modeling clay on the bottom of the landfill to simulate a seal. When a landfill is closed, the top is sealed to prevent precipitation from adding more liquid to be leached. Some chemicals are good for crops. The right amount at the right time will increase growth, but sometimes too much fertilizer is put on crops in the field. When we put this paper towel down to represent a crop and add dye to simulate fertilizer, we can see that some chemicals are used by the plants. If too much is applied to the field, it can run off the crop into the groundwater and into our wells and lakes and streams. The problem is not just fertilizers on crops, however. If we dump a paint can or spill some oil or gas, it just might end up in the glass of water we get from our faucet. Groundwater is one of our most important water resources. It can be overused and abused so that it no longer is able to meet our needs. If we want to continue to have abundant, safe, and clean groundwater, we need to ensure that it is properly used and that it will stay clean for generations to come. For more information about how you can help protect our groundwater, contact your local county agent or the nearest office of the United States Environmental Protection Agency.